In this lecture, we're going to talk about determinants. So, suppose we had a matrix, and you had the idea that you'd like to essentially pack as much info as possible about this matrix into a single number. So we're going to associate a number to a matrix that's going to sort of capture as much info as possible about that matrix. Well, that's exactly what a determinant is. So the first thing I want to note is that we will only be considering for this lecture square matrices. Okay, so n by n matrices. Or linear transformations. What would our linear transformations look like that correspond to square matrices? Well, they'd go from Rn to Rn, right? The same space. Okay, so let's just keep that in mind. Before I tell you mathematically what a determinant is and what the formula for it is, I want to start with the geometric intuition. So it has a really nice geometric meaning. So here's the geometric intuition. Let's start with the two-dimensional case. So we're going to have a transformation from R2 to R2. And this will be a linear transformation, of course. And that transformation will be given by a matrix, multiplication by a matrix as usual. So T of x is A times x. What kind of matrix is A, by the way? Well, it's a square matrix, right? It's a 2 by 2 matrix in this case. That's a 2 by 2 matrix. Okay, well, what is a determinant? Then the determinant, we say the determinant of a matrix, not a linear transformation. So the determinant of the matrix A is, it's an area. So it's, actually I should say it's the signed area. I'll tell you what that means. But yeah, it's a kind of area. And what is it the area of? It's the area of what you get by starting with the unit square and then applying the transformation. And that sort of shifts the unit square into a different shape. So how can I say that? It's the area of the image, right? The image of the unit square under T. Under the transformation T. Okay, let's look at an example. Oh, by the way, I'll tell you about the sign part in a second. So let's immediately look at an example though. So what if this were my matrix? 2, 1 is the first column, and then 1, 3 is the second column. Okay, and some of you might have seen a formula for determinants, but pretend you don't know the formula. We're just going to solve this geometrically. So what would be the determinant of this matrix? Well, this represents a linear transformation, right? So let's draw a picture of this linear transformation. It's going to, actually let me go down here. And we're going from the same space to itself, but I'll draw it over here. Okay, so applying my transformation. What do we mean by a unit square? So the square with side length 1. Okay, so there's my vector 1, 0. It's a square formed by the two standard basis vectors. And here's my vector 0, 1. And what square am I talking about? Well, it's this square right here. Okay. What's going to happen to that square? Well, this matrix tells me everything, right? Because what is this vector 2, 1? That's where 1, 0 gets sent. So that's right here. And then what about this vector 1, 3? That's where 0, 1 gets sent. So let me draw that in red. So that's this vector here. Okay, well, what about this point here? Well, that will get, because t is linear, that will get sent to, that's the sum of 1, 0, and 0, 1. That will get sent to the sum of these vectors, which you can find just by making this parallelogram, like we've done before. So we get this kind of shape. It's a parallelogram. Yeah, I'll write that. It's always going to be a parallelogram. Or not always. It could get crushed down to a line or to a point or something like that. Yeah, this is the vector 2, 1, and this is the vector 1, 3. Well, what's the area of this parallelogram? How would you do that, by the way? Can we just do it? Can we just look in this picture and figure it out? Here's another color, maybe. So maybe what we can do is we can draw this bigger rectangle here. And that whole rectangle is 12. Okay. So the area is going to be 12 minus some stuff. So I see 1 square there. I see 1 square here. I see this is a triangle with 1 and 3 side lengths, and there's another one there. You see, if I fit this one together with this one, I'll get a 1 by 3 rectangle. So I need to subtract off. I'll subtract off those 2 squares, and I'll subtract off the 1 by 3 rectangle from these two. And then I see a triangle there, a triangle here. If I fit these two together, I get a 2 by 1 rectangle, so I'll subtract that off also. So what do we get? 12 minus 2 is 10, minus 3 is 7, minus 2 is 5. Okay, so 5 is my determinant. 5 is the determinant of A. Okay, so it's basically how does my transformation scale area? Okay, so it scales it by a factor of 5. Start with an area of 1, I end up with an area of 5. What if I have this matrix? So 1, 3, 2, 1, like that. So I just swap the columns. Well, you see what happens is I mean, I won't draw that picture again. But what do we get over here? We get the same picture, but this blue one actually goes to the red one. So I'll draw the blue one here. Okay, so here's my new transformation. And the red one actually ends up over here. So you see what happened is I reversed the orientation. Okay, here the red one was to the left of the blue one, and here it ends up on the right of the blue one. So we would say, T reverses the orientation. Okay. That's what I mean by signed area. Okay, so if it reverses the orientation, you have to put a negative sign. So the determinant of this A, and that's my definition. That's my notation for determinant. It's det of a matrix. In this case, it would be negative 5. Because you get the same parallelogram as the previous picture, but I've flipped the orientation. Okay, let's do a few quickly. So, well, how about this one? Can you tell me what the determinant of the identity matrix is? I start with an area of 1, right? I apply the identity transformation. I still get this picture, right? So it's 1, right? I don't change the area at all. Or I scale the area by a factor of 1. Let's do another example. What if I have this one? 1, 0, 1, 1. Okay. What is the determinant of this one? Okay, well let's draw a picture really quick. This is actually a pretty important transformation. This is called a shear. So again, this is our starting picture. And you see 1, 0 just stays where it is. That's what the first column's telling me. 0, 1 gets sent to 1, 1, so it'll get sent there. Okay, so I get this shape. Again, a parallelogram. That's where the unit square gets sent. But you see, this also has area 1. So the determinant of this A is also 1. Okay. So we immediately see that a determinant is not unique, right? These are two different matrices that both have a determinant of 1. And in fact, another example would be any rotation matrix would have a determinant of 1, right? Because we'd start with the unit square and then we just rotate it, but we're not changing the area. Okay, so there are lots of matrices with any given determinant. We'll just keep doing examples because it's fun to think about. So what if I gave you this one? I'll tell you the mathematical definition soon. What's the determinant of that? And again, even if you've seen the formula, think geometrically. Okay, the determinant of this one is 12. Why 12? Because we're stretching this one by a factor of 3, and we're stretching this one by a factor of 4, right? And so we get a 3 by 4 rectangle, which is going to have area 12. Okay, one more. And then I'll tell you the formula for a 2 by 2 case, which a lot of you have probably already seen, but let's do this one. 2, 1, minus 4, minus 2. Okay, where are my standard basis vectors going to end up here? Let me draw a graph. Okay, so my vector 1, 0 gets sent to 2, 1. That's this vector. And then 0, 1 gets sent to minus 4, minus 2. Use my ruler. Not convinced I can draw this straight. Okay, so I'll be here. Oh, but look what happens. So they're both getting sent to the same line. Okay, through the origin. Okay, so this is, and we can see that, right? Because the columns of this matrix are not linearly independent, right? So this is not an invertible transformation. It's not one-to-one. There's going to be some collapsing down involved. So we actually collapse this unit square onto this line. I mean, I want to shade it in a slight blue color like I did up here, but I can't do it, right? Because it's just, this is what happened to the square. So what will we say the area of that square is? Well, it's 0, right? or whatever shape it is. Yeah, it's 0, right? So this is a determinant of 0. So yeah, what does determinant of 0 mean? Well, it means that your transformation was not one-to-one. Right? It means that there was some collapsing involved. So my two-dimensional square got collapsed down to a one-dimensional object. Or I mean, here's another example with determinant 0. This is an extreme example, but it's always helpful to think of extreme examples. The matrix just, sends everything to 0. That's another example of determinant 0. In that case, everything will get collapsed down to a point. Okay, I promised you the formula. So a formula for the determinant of A, where A is a 2 by 2 matrix. So let me write it out. Let's put A, B, C, D for the entries. Okay. It's important. And by the way, how do you get this formula? Well, you just sort of do the same parallelogram thing. You draw, I guess, AC and BD, and then you try to do what I just did here in general. But what you get is, after a bit of work, is that a determinant of A is AD minus BC. Okay. Okay. What can we say about this? So, well, let's look at some previous examples just to see. So AD minus BC. How about this one? Do we get 5? That was what we were supposed to get. 6 minus 1 is 5. All right, so we do get 5. Here we get 1 minus 6. That's negative 5, which is what we said. This one we get minus 4 minus minus 4, which is 0. So that's the determinant of 0. So very handy formula. This only works for a 2 by 2 case. But here's an application. And we can actually use this idea of determinant to find areas. So we can kind of do it the reverse. If we have the formula, let's say I give you this problem. So what's the volume of a triangle? I'm going to say, wait a second, triangle? We're talking about parallelograms. But okay, volume of a triangle with vertices 0, 0, 2, 4, and 5, 7, let's say. Okay. Well, what's the picture? I mean, I'm not going to draw it carefully, but we have 0, 0, and then we have some vectors, right? So maybe this one's 5, 7, and that one's 2, 4. Well, we can notice that that's sort of half of our parallelogram that we get. The full parallelogram might look something like that. So this is going to be half the area of, so the area of this triangle, of the triangle, let's say, is going to be half the area of this parallelogram. What is the parallelogram? We can interpret that as the area of the parallelogram as the determinant of the matrix that starts with a unit square, right? And then we just send 1, 0 to 5, 7. And then we send 0, 1 to 2, 4. Okay. By the way, here's another notation for a determinant that I'm going to use later. We can denote this by 5, 7, 2, 4. That's the determinant of this matrix. You might say, oh wait, I just wrote down a matrix again. But no, you see how I made these lines just straight lines. I didn't put the brackets on them. Okay, so when you have straight lines on both sides of the matrix, that means determinant. Okay. So what's the determinant of this matrix? Well, it's 20 minus 14 by the formula, which is 6. That's half that, right? Because I'm just taking that triangle, so I get 3. Okay, so we can use determinants to calculate areas if we have the formula. Okay, but that was just in 2 dimensions. So what about 3 dimensions? So then, as usual, it's going to be harder to imagine for greater than 3 dimensions, and we're just going to have to rely on the mathematical formula. But yeah, let's say we have a transformation from R3 to R3. Again, we're just going from the same space to the same space. So what's the determinant of a matrix? A, associated with the transformation. Well, it is the, not area this time, but volume. I'm sure you would have guessed. It's the volume of the image of the unit, not square, but cube. The unit cube under a transformation. Okay, cool. So it still has a really nice geometric meaning. Do I dare try to draw this? Okay. I have my basis vectors here. I'm going to try to draw them. I need another color. Let's do green. Okay, and then we're going to do the transformation. So again, we have like a cube here. It's my unit cube. Something like this. It's a cube. And then we do our transformation. And what do we get? Well, still my coordinate axes here. But let's say the blue one ends up here. And the red one ends up here, something like that. Let's say the green one goes somewhere crazy, like way over here. Well, what shape do we get? Okay, what happens to the unit cube? Well, let me try to sketch it. Okay. It's not a parallelogram. That's a two-dimensional shape. Sort of it's a slanted cube. You could call it that. I think the official name for this is a parallelepiped. I'll write that word down in a second. I think we have that one going down there. Okay, how did I do there? Could have been better, but you can kind of get the idea. So this is a parallelepiped. Probably spelled that wrong, but that's what they call that shape. And again, yeah, what would the determinant is the volume of this parallelepiped. That's the geometric meaning. What would it mean for the determinant to be 0? What will mean that this cube gets squashed down into the two-dimensional plane, or a one-dimensional line, or even a point. Right? Okay, but above 3 dimensions, it's impossible to visualize this. We'll need to come up with a new name for the 4-dimensional analog of the parallelogram. So let me tell you, actually, the mathematical definition of determinant. Yeah, this is a geometric intuition. Don't forget the geometric intuition. It's very important. So here's a definition of determinant. In terms of mathematical symbols. Determinant. Okay. This is going to take some time, actually. It's pretty complicated. Because it's so complicated, I'm going to write it down, and then we're just going to immediately do an example, and it'll make a lot more sense in the example, probably. So we're going to let A be a matrix. Not just any matrix. Square matrix. So an n by n matrix. Okay, so what is A going to look like? Well, we have entries, I'll call them A11. The typical way to do this is to have 2 indices. So that's not A11. That's A11, meaning first row, first row, first column. So it should be A12 all the way over A1n. Now if we go down, we have A21, A22, A23, etc. A31. Okay, you get the idea. Okay. First thing I want to do is I want to define the cofactor of an entry in this matrix. But I think I'll need to do that in 2 steps. So I'm going to let Aij is going to be something very specific. So this is going to be the submatrix, and it's actually going to have dimension 1 less. So n minus 1 times n minus 1, or by n minus 1, submatrix formed by deleting the ith row and jth column of A. Okay, so take out the ith row, take out the jth column. You have a matrix that's 1 smaller in each direction, 1 dimension smaller. Okay, and that will allow me to define the cofactor. So next, given any entry in this matrix, we can define its cofactor. Okay, so that's a new word, so I'll underline that. The cofactor of some entry, I'll call it Aij, little aij, to be. Okay, so I'll give that a name. I'll say it's Cij. I'm defining it to be minus 1 to the I plus j power. And this looks complicated, but it's actually something very simple. I'll show you in a second. Times the determinant of the submatrix you get by deleting the ith row and jth column. So in other words, the determinant of this Aij. So for example, A23, if I want the cofactor, I delete that row, I delete that column, take the determinant of the resulting matrix, and then I have to multiply by -1 to the 2 plus 3, which is -1 to the 5, which is -1. Essentially, this is just, if I plus j is even, this is going to be 1. If I plus j is odd, that's going to be a -1. Okay, I'm almost there. So then the determinant, what is the determinant actually? And you might be saying, well, wait, this is circular, right? Because I already used the determinant there. So it's not circular, actually, because it's going to be a recursive definition. But a determinant of A is the number. It's the following number. Okay. The cool thing about this is you can pick any row you want or any column you want. So let's pick the ith row. Pick row I, and then we do the following. We go across that row. We just look at all these AIs. So we do AI1 times its cofactor plus AI2 times its cofactor. And again, I'm going to do an example, and this is going to make much more sense. Plus AI going all the way across the row times its cofactor. Okay, so there are a lot of cofactors here. So this is called the cofactor expansion along row I. We can do it along any row, or so I'll say or I could do it along any column. So let's do it along the jth column. So then I have A1j C1j plus A2j C2j all the way up to I'm getting confused, ANJ times CNJ. Okay, and this is called cofactor expansion. And again, you're allowed to pick. So you can pick any row or any column. It turns out you will always get the same number when you do this. So pretty amazing. And that's called a determinant of the matrix. Okay. So first of all, let me address this issue. So why is this not a circular definition? Well, it's because this is the determinant of a matrix that's one dimension smaller. Okay, so you recursively apply this procedure until you just get down to 1 by 1 matrices. I have to tell you remember we need a base case for recursion. So the determinant of a 1 by 1 matrix is just its whatever the number is. It's just its entry. Yeah, it's just its entry. Okay. Yeah, let's do an example. So, I mean, we can even try to get a formula for the 3 by 3 case now. So, a 3 by 3 matrix. I'll stick with these A's just so we can sort of match that up with these. And then I'll do an example with numbers. A12, A12, A13. And this is A22, A23, and A32, A33. Okay, what is the determinant? Well, we can choose any row or column. So we'll choose row I equals 1. So I'm going to use this first formula. Okay. So the determinant of A is A11 times C11 plus A12 times C12 plus A13 times C13. Which is okay. A11 times, let me actually box this, the cofactor, because I'm going to be looking up here a lot probably. So yeah, I need to know what the cofactor is. Okay, so what is the cofactor? It's -1 to the 1 plus 1, which is 1. Right? -1 to the 2 is 1. So I have a times 1 times the determinant of, so I'm going to use that bar notation that we talked about, just straight lines. The determinant of Aij. Aij is a matrix formed by deleting the ith row and the ith column. So in this case, I want to delete the first row and the first column. So just imagine this, right? I want to take the determinant of that matrix. So I'm going to write down that matrix. A22, A23, A32, A33. Plus, Now I go across. I go across the row. So that's what I'm deciding to do. So A12 times this part. Don't forget the minus 1 to the power of 3 in this case, which is minus 1. You know, what's going on with that negative? If you don't like this negative 1 to the I plus j, just think this way. You start with a plus up there, and then it's a checkerboard pattern. Or chessboard, if you prefer chess. Yeah, so it's just going to alternate pluses and minuses. So I need to take the minus for this one and a plus for that one. Okay, and we'll multiply that by A21, A23, A31, A33, this determinant. How did I get that, by the way? I deleted the first row, second column. Right? And I just say take the determinant of the resulting 2 by 2 matrix. Plus A13 times 1 times, right, it's a plus, A21, A22, A31, A32. Okay. What is this actually going to equal? Well, it'll be A11 times 1 times the determinant of this. We already have a formula for the 2 by 2 case, so we can just use that. So it's A11 times A22, A33, minus A23, A32, plus, I have a minus 1, so I'll just write minus A12 times A21, A33, minus A23, A31. I'm getting tired of writing this, but I guess I'll finish. Okay, and then times A21, A32, minus A22, A31. Okay, that's the formula for the determinant of a 3 by 3 matrix. This is getting very long very fast, right? This is 2 by 2. This is the 3 by 3. Imagine how long the 4 by 4 one will be. Okay, so I promised an example with numbers, right? So let's put some numbers to this. So let's suppose we have the following matrix: 1, 2, minus 4, 5, 0, minus 2, minus 1, 0, 1. Okay. So let's do this 2 different ways. So we can first expand along row 1 like we just did before. And I wouldn't use this formula. I would just do it again from the matrix. It's often easier. So I'm doing 1 times the determinant of this one. You've just got to do several. I didn't want to put that bracket there because I really do want to mean determinant. Right? So it should be straight lines. Minus 2 times. Why did I put the minus there when it was a plus 2? Because of the I need that in the cofactor, right? So it's a minus 2 times 5 minus 2 minus 1, 1. And I have a plus negative 4 times 5, 0, minus 1, 0. Okay? And I was just going to say, you've got to do several examples of this, and then once you do, it'll just click, and it'll be easy from there on out. But it takes a lot of practice to be able to do this accurately. Okay, so this ends up being 1 times 0 times 1 minus 0. Yeah, so I have 0 minus 2 times 5 times 1 is 5 minus negative 2, right? Or sorry, minus minus positive 2. So what's that going to be? That's going to be 3. And then I have minus 4, 5 times 0 is 0, minus 1 times 0 is 0. So I'll just be times 0. So what do I get? I guess I just get negative 6 for my determinant. Okay. There's often a way to make things easier for yourself. So what if I instead, the idea is if you see a bunch of zeros in a row or a column, like I see this column 2 has 2 zeros in it. See, those are going to be these entries here. So it doesn't matter what this is or what this is. So you should take advantage of zeros. So I'm going to actually expand along column 2 just to show it's a little bit easier. You should still get the same answer, so we should still get -6. Okay, how does this work? I go down this column, so I'm going to do 2 times. Now delete the row in the column that has the 2 in it. But wait a second, I missed something, right? I'm supposed to use the minus. Right, because this is entry 1, 2, okay? -1 to the 1 plus 2 is -1 to the 3, which is -1. So I have -2 times 5 minus 2 minus 1, 1, plus this 0 here times something I don't care about, plus 0 times something else I don't care about. Or I guess I technically should say -0, but I don't really care, because -0 and plus 0 is, yeah, I'll just write something. Stuff. It's 0 times some that stuff, so it doesn't even matter. So my determinant is just this part. Okay, which equals -2 times, what is this going to be? 5 minus 2, which is 3, so -2 times 3, which is -6. Okay, so take advantage of rows and columns that have lots of zeros in it. It's the moral of that story. There's another case where the determinant is really nice to calculate, really easy. So I'm going to give you a scary looking matrix, 4 by 4. Hard to think about the geometric intuition for 4 by 4. This is going to be the matrix. It's 4, 7, 2. Actually, doesn't matter too much what numbers I put there. -2, put 12, 0, 0, 0, 5. Okay. This is a special kind of matrix. Okay, so this is an what I would call an upper triangular matrix, or you could just call it a triangular matrix. Upper triangular matrix. Upper triangular is more descriptive. So what do I mean by upper triangular? All entries below the diagonal are 0. By diagonal, I mean this diagonal. All entries below that diagonal are 0. So that's upper triangular. It's got to be this diagonal. The one that goes from top left to the bottom right. But all entries below that are 0, so that's an upper triangular matrix. A lower triangular matrix, these could be any numbers, but then these numbers above the diagonal would be 0. Okay. Okay. If we have a triangular matrix, formula for the determinant is really nice, but let's see why. So the determinant of A is going to be, let's see. Remember, let's do it along the first column. So I'm going to do my cofactor expansion along this column. Take advantage of the 3 zeros. So I've got 1 times, and I don't need a sign. I just need a 1 there, because that's entry 1, 1. Times the determinant of this matrix. -4, 7, 2, 0, -2, 12, 0, 0, 5. Now we have a new determinant problem. What's the determinant of that 3 by 3 matrix? It's going to be 1 times. Again, let's expand along this first column. So it's 1 times this -4. Again, that -4 is in the top left entry, so it's going to have a plus sign in the cofactor. So -4 times a determinant of this 2 by 2 matrix. Plus, I have 2 other terms, but they're both 0, right? Because as I go down here, I get 2 terms that are 0 times something and 0 times something. So that's it. But what is this? I mean, we can do this. We don't have to use it. We can use the 2 by 2 formula if we want. But we can also just say, now expand along this column, and we get -2 times the determinant of this 1 by 1 matrix down there. So I'll write the 1 by 1 matrix 5, and it's plus 0 times, I guess -0 times something, doesn't matter. Okay, but this is just 1 times minus 4 times minus 2 times, what's the determinant of matrix 5? Just 5. So this equals 40. Did I do that right? It's number 40. What did we just figure out here? Fact. We're going to see a bunch more facts about determinants in the next 10 minutes or so. But the determinant, here's our first fact. The determinant of a triangular matrix. It can be either upper triangular or lower triangular. But the diagonal's got to go down this way, right? But the determinant of a triangular matrix is, what did it end up being? It's just a product of the diagonal. It's the product of the diagonal entries. Okay. Very cool. So, okay, now that we're talking about facts about determinant, let's look at some of the most important properties of determinants. Okay. First of all, what is the determinant of... There's not a nice formula for a determinant of A plus B, it turns out. Okay, when you add two matrices. But there is a nice formula for this. Determinant of A times B. Here's one way to think of this. If we go back to thinking about areas, it's kind of a cool way to think about it. So, what is AB? It's a linear transformation that means you first do B and then A. Right? Matrix multiplication is composition of linear transformations. So let's say B scales by a certain factor and then A scales by a certain factor. So B scales area by a certain factor. What is that factor? It's determinant of B. And A scales area by a certain factor, which is determinant of A. And I mean, we have to keep in track of the orientation too, right? So there might be a minus sign. But then what will their composition scale area by? What will be the product of the two factors, right? The product of the two scale factors. So it should be determinant of A times determinant of B. And it is. This is not very easy to check using that formula, but it's possible. But just thinking about how determinant scales area or volume, if we're in 3 dimensions, allows us to basically just write this down immediately. So this is a true property. How about the determinant of the inverse of A, assuming A is invertible? If A is not invertible, so it'll be 0 if, well, I mean, it's never 0 actually, because if, I'm assuming we can take A inverse to even write that down, right? This doesn't mean anything if I can't take A inverse. Yeah, but if A is not invertible, then our determinant is 0. But otherwise, the determinant is, well, if A represents the transformation that scales area by determinant of A, what does A minus 1 represent? It represents the inverse transformation. So it sort of scales the area back. So if A was scaling by 5, scaling area by a factor of 5, and A inverse would be scaling area by a factor of 1/5. Okay. So this should be 1 over whatever the determinant of A is. And again, that is a true thing. Okay. How about determinant of? Oh, by the way, you can deduce this from the first property. That's because A times A inverse is I, right? The identity. And if I take the determinant of both of these, take the determinant of both sides. Well, I is it's a diagonal matrix, but it's a triangular matrix in particular. It's more generally a triangular matrix. So the determinant is just the product of all the ones, which is 1. And here we get a determinant of A times the determinant of A inverse by the first property. That equals 1. If I divide by that determinant of A, I get 1 over determinant of A. Similarly, this is another one we could just deduce from the first property. Determinant of a power matrix is just, well, it's just this, right? So you take the determinant of A and you multiply it by itself n times. Ooh, here's one you have to be careful about. Determinant of a constant times a matrix. What is that? A scale matrix. It is not C times the determinant of A. So it's not this. Why is it not this? It's because when you multiply a matrix by a scalar, you're scaling every entry of A. Right? So it's like the linear transformation. When you're sort of scaling every one of these vectors by a factor of C. Right? So it needs to be, so I'm scaling n vectors, right, if I'm in Rn, by a factor of C. So this should actually be C times C times C n times, or C to the n. Okay, so this is one you have to be a little bit careful about. It's not C times determinant of A, it's C to the n. What is n? So n if A is n by n matrix. Okay. Okay, let's do a quick example. Just how would you use these properties? So find a determinant of the following matrix: A inverse times B cubed. If I'm going to tell you the determinant of A and B. Determinant of A is 5, and the determinant of B is 10. Okay, let's write it down. So determinant of A inverse times B cubed is by the first property and the third property. Let's do them both at once. So determinant of A inverse, or I won't do them both at once. So it's determinant of A inverse times the determinant of B cubed. But the determinant of A inverse is 1 over the determinant of A. I mean, a clever way to write that would actually, sorry if this is confusing, but it's kind of a clever way to write this, right? Because this is a reciprocal of the determinant of A. So det of A to the minus 1 is det A to minus 1. This minus 1 in this case means reciprocal, whereas that minus 1 means inverse. What's this one? What's the determinant of B cubed? Which is 5 to minus 1, which is 1/5, times 10 cubed. So 1,000 divided by 5 is 200. Cool. Okay. Oh, so what's the most important fact of all? So the determinant, so very important. So the determinant, it's this one number. It has a lot of information. For example, it tells you how the linear transformation is changing area or volume. It's telling you whether it's flipping the orientation with a negative sign or a positive sign. But probably the most important thing is, what does it mean for the determinant to be 0? Well, we already kind of discussed it. But in general, it means that the transformation is not invertible. You can't do it in reverse because there's some collapsing down. So this matrix A is not invertible. Okay, and that implication goes both ways. So if we have a transformation that's not invertible, then the determinant of A is going to be 0. We could also write it this way. So we could say, well, when is the determinant non-zero? It's non-zero exactly when A is invertible. The only reason I want to write it that way is so I can add it to our unifying theorem. So remember, this is exactly the situation where we have a square matrix. We have n vectors in Rn. The linear transformation is going from Rn to Rn. By the way, I added these two from last time. I don't think I did in the video, but I mean, the nullity of A is 0. That's clearly equivalent to the kernel just being 0. Right? I have a 0-dimensional null space. And the rank of A being n, that's the same as the image of the transformation being Rn. The columns span all of Rn, so the rank is n. But we can add number 11, Okay, because number 6, if A is invertible, then the determinant of A is 0 or non-zero. If A is invertible, the determinant is non-zero. Okay? The determinant of 0 means that I cannot invert it. Right? I'm collapsing, a three-dimensional space to a two-dimensional space or something like that. Okay, this one is super important. Let me even want to distinguish this in some way. So why is this so important? It's because this is just a number we can calculate with a formula. Right? You just calculate a determinant, and that tells you if the determinant is non-zero. Look at all the things it tells us. So in practice, this is often the most useful one. If you know the determinant is not zero, we know that ax equals b has a unique solution for every vector in Rn, for every vector b in Rn. And we know that the transformation is 1-to-1 and onto. We know what its kernel is, we know the nullity, we know the image, all these things. Okay. Likewise, if the determinant is 0, we know that t is not onto. It cannot be onto, or the columns have to be linearly dependent. And we can say all these other things about the transformation. So, this one is absolutely key. Okay, because again, determinant is just one number that you can calculate from the matrix. Okay. Do I have anything else to talk about? Let's see. One other thing I wanted to talk about. I'll do this quickly. But how do row operations affect the determinant? It's actually something really nice we can say about each of the row operations. How did it affect the determinant? They change it in a very predictable way. Okay. All right. What should we do first? How about multiplying a row by a scalar? That was a row operation. So multiplying a row, and again, we're only talking about square matrices. Right? So multiplying a row by a scalar, C, let's call it. So some scalar, just a real number. What does it do to the determinant? It also multiplies the determinant by that number. If we multiply every single row by the scalar, then we multiply by the determinant by c to the n, which is what this property was saying. But we just multiply one row by a scalar, we also multiply the determinant by that number, so that's really nice. What about swapping two rows? That multiplies the determinant by a -1. So it just swaps the sign of the determinant. If I swap two rows, I swap the sign of the determinant. Then if I swap two more rows, I swap it back. All right, I swap the sign back. Okay. And the third one, adding or subtracting a multiple of a row to any other row. I should say 2 from any other row. What does that do? It turns out that does not change the determinant. That's surprising, because this seems like the more complicated of the three. That doesn't change the determinant. You can try to think about why that's true, using the what we've talked about so far. It doesn't change the determinant. Okay, so these are really important. Why are they so important? This actually gives a really efficient way to calculate determinants. So here's an efficient way, and this is how computers, well, I shouldn't say for sure this is how computers do it, but this is one way that computers can do it very quickly, compared to at least the definition that we had. So this is an efficient way to compute determinants. What do? You apply row operations to your matrix A until you get, well, what's it going to look like in the end when we do all the row operations? Well, there might be some free columns, right? Might not be an invertible transformation. But let's say there aren't any free columns. We just get we get pivot, 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 and then we have all these zeros down here. Then we have other stuff up here. This can be any numbers. So what kind of matrix is that? That's a triangular matrix, right? Until you get a triangular matrix. It's an upper triangular matrix, in fact. And as long as you keep track of the operations, and the effect they have on a determinant, well then, when you get the upper triangular matrix, it's obvious what the determinant is. Right? It's just the product of the diagonals. So let's suppose I swapped two rows, and then I just did a bunch of this step, adding and subtracting a multiple of a row to another row. That doesn't change the determinant, but I have to remember that I swapped those two rows. So I multiplied it by -1. So I need to take the determinant of this matrix, just multiply these entries, and then I need to remember that I multiplied by -1. So I need to divide by -1. Well, that's just the same as multiplying by -1. And I get the determinant of the original matrix. Okay. And it turns out this actually has, so if you're into computer science at all, this method for computing the determinant, if A is an n by n matrix, this has time complexity big O of n cubed. That's Gaussian elimination. That's the complexity for Gaussian elimination. Whereas, what is the complexity of this method? Okay, this recursive method. This is again something that's very easy to program because recursion is very natural to program. Anytime you have a recursive algorithm or recursive formula. But unfortunately, this is going to be O of n factorial. Because imagine we had a 4x4 matrix. Well, we'd have 4 terms here, but then each term would involve a 3x3 determinant. So there'd be 3 terms. But then each of those involve a 2x2 determinant. So we have 4 times 3 times 2 times 1 terms. So this is O of n cubed versus O of n factorial. Okay, and that one's way better. Well, certainly as n gets large, right? This one is way better than that one. Okay. So this is another way you can consider calculating your determinants. Okay, so really we're talking about determinants so that we can next talk about the most exciting part of this course, which is eigenvalues and eigenvectors. So that's what we're going to do next. Thanks for watching.